In this segment, I'll look at a way of returning our search results faster, a more efficient way to traverse postings lists to get out our answers, and that's by making use of skip pointers. So you should remember the basic merge algorithm. So in the basic merge algorithm, we had these pointers and we were walking simultaneously down these two postings lists, returning the things that matched in time linear in the total number of postings entries. The question is, can we do better than that? And the answer is that if our index isn't changing too fast, it's not a very dynamically changing index, and so it's profitable to do a bit more work in advance, that yes, we can do better than that. And so how do we do that? Well, the idea of that is at indexing time, we augment our postings list by these extra pointers, which are referred to as skip pointers. And so those bits in purple and blue up the top are skip pointers. And the idea of that is, in certain circumstances, we'll be able to work out that certain documents couldn't possibly appear in the results listings, and then we'll know that we can just skip right past them, and therefore we'll spend less time walking down the postings lists. And so the two questions then are, well, how exactly do we do that, and where should we place these skip pointers? And so this is an example illustrating how we're going to do it. So we're imagining that we have these two pointers going down the postings lists, and at the moment they're both pointing there. So at this point we say for an AND query, okay, document 8 is a match because the term appears on both postings lists. Great. So we put 8 into our result set, and then we're going to go on. And so the way we go on is by, in our previous algorithm, we advanced both pointers to the next document. Okay, and then at this point, we would say which of these two is smaller. And which one is smaller is 11. But rather than just going on to 17 as we normally would, what we can do is instead also consider the skip pointer and say, look, if you look at where this skip pointer goes, the next thing the skip pointer goes to is 31. And 31 is also less than 41. And so therefore, rather than advancing to 17, we can actually advance all the way to the thing that's next after the skip pointer. That whatever is here is actually the next potential document match that could possibly match or not match with 41, 48, or one of the things that comes after it. And so because of that, we've been able to skip over dealing with a whole bunch of the things that were on this list. We just know that these things aren't going to be matches. So that's the idea of how you can gain. In the details then, there's clearly a trade-off, that if we have a lot of skips, then we're likely to be able to follow the skip pointers and therefore not do a couple of step along lists and matching in the merge algorithm. But on the other hand, we're still going to be doing lots of comparisons. We'll just be doing them to skip pointers, and we normally won't be advancing very far each time. If we only just put in a few skips that are big long skips, well, then we're not adding many pointer comparisons, and when we do skip, we get to go forward a long, long way. But on the other hand, we probably won't be able to successfully skip very often. The traditional heuristic for how to place skip pointers was that for a postings list of length L, we used square root of L evenly placed skip pointers. And that was the heuristic suggested and validated in the original paper by Moffat and Zobel advocating the use of skip lists. But it's a convenient, easy heuristic, but it ignores the distribution of query terms, and it is possible to come up with better heuristics, and people have worked on that in later research papers. But the final point I just want to mention at this point, as one will come back to it in various places, is Well, are skip pointers and skip lists useful at all for speeding up an indexing system? So at one point, it definitely used to help a lot using skip lists, and you can find that in this original Moffat and Zobel paper. But it turns out that what helps or not is very dependent on very particular hardware assumptions. And so a lot of the time that if you've got your postings lists on disk and that you're going to be getting them into memory as a stream to satisfy your query, well, it turns out that the transfer of information from disk to memory is sufficiently slow that the number one determinant of performance is making the amount of information that's transferred as small as possible. And adding skip pointers increases the size of postings lists, even if only a little. And so this paper from 2002 came to exactly the opposite conclusion. It was saying that in modern situations, that the I/O cost is sufficiently high that it's not worth using skip lists. But, you know, that then changes around again with different assumptions. So there's actually a newer 2007 paper that says no, under this architecture you can get a lot of value from skip lists. And while these days people are increasingly starting to use flash for storage rather than hard disks, and that obviously has very different characteristics than the assumptions of hard disks. So a lot of these things are very system architecture dependent, and what's optimal keeps on changing as the details of our computer systems change. But despite those warnings about how it may work or may not work, this is one of the good techniques to know about for ideas of how to speed up doing the merge algorithm for efficiently answering queries. And actually it turns out that skip lists are a good general computer science idea. So they've actually been discussed in the algorithms literature. The skip list can give you all the advantages of tree-based data structures in a fairly simple and efficient manner.